Okay then, so in this video, we're going to be looking at a typical Arrhenius equation calculation. This is from an Edexcel past paper, but the principles are exactly the same for all exam boards. Essentially, we have to be aware of just how to rearrange this expression and then be able to solve it for which variable they're requiring. So hopefully I can explain myself and it becomes a bit more clear. So let's jump straight into the question then. So the rate constant is going to be K, not this K, this is Kelvin, for the decomposition of nitrogen oxide was determined at two temperatures. So we have temperature 1 here, I'm just going to label that T1, and this is temperature 2, T2. We have to calculate the activation energy for this reaction. We have to include units and give our answer to an appropriate number of sig figs. So here I'm seeing 3, 3, 3, and 3 sig figs. So I'm just going to give my answer then to 3 sig figs. All right, perfect. So it says you should not attempt to use any graphical method in order to answer this question, and the Arrhenius equation relating two rate constants K1 and K2. So again, I'm going to do the same thing that I did for temperature. I'm going to call this K1, I'm going to call this K2. At two different temperatures can be expressed as this. Right then, so what do you think we have to do here? What I'm going to ask you to do is pause the video. Hopefully you have some fundamental understanding of Arrhenius, temperature, and kinetics, rate equations, stuff like that. And you can pause the video, attempt it yourself, fill in the blanks of my explanations. But if not, go ahead and watch and I'll explain everything for you. So then, what we're going to do first is this is our equation here now. R, this is 8.31. I'm going to actually write that up here. R equals 8.31 joules per Kelvin, that's a capital K, per mole. Now, this is given to you, I believe, in the data sheet for Edexcel and OCR, but normally in AQA it's going to be given to you in the question, so you don't need to remember it, but that's 8.31. What is useful to remember is the units. Just remember these off by heart. At this point, you've been doing ideal gas, you've been doing all sorts of stuff involving this, so hopefully you just remember it. But what's really important in this topic, because we're dealing with activation energy, which is actually what we're looking for here, this EA, this is always going to be a unit of energy. So it's either going to be joules or it's going to be kilojoules. So we have to make sure that we convert where appropriate. And this applies to all content and all topics which require energy in the equation. So let's jump straight into this. And then, so hopefully your rearranging abilities are pretty up to standards here. So what I'm going to be doing is just rearranging this. So if we want to get our activation energy, ultimately we have to make our activation energy the subject of the equation. So then let's just jump straight into this. So if I do, what I'm going to do first is just take our R constant, our gas constant, to the other side of the expression. So that's going to be minus EA multiplied by 1 over T2 minus 1 over T1 equals, and this is just going to be our R multiplied by, I'm just going to use the dot there if you're not familiar with that, ln and then K2 over K1. So I haven't really done anything too fancy here, just rearranged the expression just to get EA as a subject. Now I'm going to be showing all my working here. You may not have to show every single step that I demonstrate, but I want to be able to explain it to you. So next up then is I'm going to be taking this portion to the other side. So we're just going to be dividing everything by that. So then minus EA equals R dot ln K2 over K1 over all over R 1 over T2 minus 1 over T1. Now, alternatively, you can skip a step here and you can actually get rid of this minus and make this a minus. Hopefully that makes sense. And I'm going to jump to that straight now in our calculation. All I'm going to do is, because we've now made activation energy the subject, I'm just going to input our values from the data table and our data sheet here and chuck it into our calculator then. So I'm going to do what I said and put a minus in front of everything. So therefore that equals minus our R gas constant value, 8.31, and this is joules per Kelvin per mole, but I'm going to leave off the units for now. And this is multiplied by our natural log of our K2 over K1. So if we just glance back at our table here, it's going to be 4.87 times 10 to minus 3 all over 1.50 times 10 to minus 3, bracket that off, and then we're going to divide that by our 1 over T2, so 1 over 338, and a minus 1 over our T1 here, 328. All right, so this is actually pretty simple, isn't it? So what I'm going to do is do this. If you put all these values in your calculator, I'm going to actually work out what this top of the fraction is, work out what the bottom of the fraction is, and write it out in one step. So make sure that you get the same values as me. But normally you can just put this all in your calculator at once. But what I find is that sometimes when you're using natural logs and exponentials, you can mess up the values in the calculators, missing brackets or all sorts, and it can actually lead to a lot of errors. So what I'm going to do is just put all our values in here. So this gives us a value of minus 9.78 6096. I've left it to a large amount of stick figures here. We'll round up later or round down as needed. And the bottom value is actually also a minus, so that's going to be 9.02 006 times 10 to minus 5. So that's our top and bottom of the fraction. So if you just put that in your calculator, that gives us an answer of 108,492.582. Now, what are our units going to be here? Now, this is in joules, so if we haven't converted anything here, our joules is going to stay the same, so it's going to be joules here. And that's per mole. If we want to, it's perfect timing to explain the units here, actually. Let me do that over here because I have a bit of space. So units then, it's going to be joules per Kelvin per mole, and that's for our R gas constant then. And then we're going to have our per second rate constant, which is here, this K2 over K1. So if we have then seconds per second divided by per second, they're just going to cancel, so I can chuck them off right there. So we're just left with joules per Kelvin per mole here, and that's over. Now, what have we got here? We've got 1 over T and 1 over T, so that's just 1 over Kelvin, which is the same as per Kelvin. Now then, hopefully you can see here that these per Kelvins also cancel, and therefore we're just left with joules per mole. So that's a little bit of explanation behind the units here. So that'll be our answer there. Now, if you look back at the question, we have to give our answer to an appropriate number of significant figures. So this isn't really going to work. For energy, when we're quoting answers to 3 sig figs, I always recommend converting this joules per mole into kilojoules per mole, just because then it makes things a lot easier. So if we divide this then by a factor of 1,000, this is going to give us 108 kilojoules per mole if we round it. So that'll be our final answer then, bush. And that's to 3 sig figs. So this is quite, for 5 marks, quite a simple question really. If you understand, if your maths abilities are quite strong, you're able to rearrange expressions and your understanding of how units cancel. Hopefully you got the same answer as me, or and a similar stages of calculation, the correct amount of significant figures, making sure to keep our units constant, whether that's joules or kilojoules. Alternatively, you could convert this to kilojoules straight away and skip this entire stage, but that's up to you, whichever you feel comfortable with. Now then, so this was a calculation Arrhenius question. The other one's going to be graphical, and I'm going to be making plenty of videos on that shortly. I hope you enjoyed the video. Be sure to like if you did, it really helps me out. Subscribe for future content. Going to be breaking down tons of past paper questions. Best of luck in your upcoming exams. Peace.